Hello. Manikanda sir, can you hear?
Yes, please.
Okay, so we can start now. So first let me introduce our speaker, Dr. M. Sabrimalai Manikandan. So who has received his BE degree in Electronics and Communication Engineering from Bhartiyar University, Coimbatore, ME degree in Microwave and Optical Engineering in Madurai, Kamaraj University, Madurai, and PhD degree in Cardiovascular Signal Processing from Department of Electronics and Communication Engineering, IIT Guwahati. He was an assistant professor for Amrita Viswavidyapeetham University, India. He was a chief engineer with the Advanced Technology Group Samsung India Electronic Private Limited in Noida, India. He is currently an assistant professor with the Biomedical System Laboratory, School of Electrical Sciences, IIT Bhubaneswar, India. He has published more than 70 research articles in reputed journals and conference proceedings. His area of interest includes signal and image processing, adaptive machine learning, the Internet of Things, VLSI signal processing, machine learning architectures, application system development, health for human machine and structural monitoring systems, audio and speech processing systems for human machine interactions, biometric and data security for authentication and authorization, environmental monitoring system for ambient assisted living, UAV assisted IoT for smart surveillance systems, and context and quality aware pattern learning networks for event recognition. So Dr. Manikandan was a recipient of 2012 Outstanding Performance Award during his tenure at Samsung India Electronic Private Limited. He served as a reviewer for many reputed journals of the IEEE, IET, and elsewhere. So he'll be talking about physiological sound analysis techniques for edge health at computing systems. So with this, I welcome sir for this session.
Sorry. This session is for speech. Yeah.
Yeah. Okay, sir, not a problem.
Okay, thank you.
So, thank you.
Thank you for introducing. And can you see my slide presentation?
Yes, sir.
Slide? I'll just go to full screen. 1 minute. Yeah, can you see my slide?
Yes, sir.
Okay. So it's good afternoon to all. Today I'll present some of our research work for the analysis of speech signal quality, in particularly for edge computing platform. So the title of the presentation is Deep Learning Based Speech Signal Quality Assessment Methods for Unsupervised Speech Analysis Systems. So the speech quality assessment not only for is for checking the quality when we do the automatic speech recognitions. It is also useful for many other applications, in particularly speech pathologies system developments. So there are many methods where we can use different signal processing techniques for assessing the speech quality, which are most important when you want to develop unsupervised speech analysis systems, in the sense that automatic systems without any human interventions. So if you see that major applications of speech processing, speech signals, one of the applications is to develop a interactive voice response systems. And you will find nowadays this interactive voice response systems in many of the e-commerce applications. So where we try to translate one language to another language. So where you will find different stages of natural language processing techniques. For example, so first we try to convert the speech into text. So that means what if I speak in English, it will convert it into English text, or if I speak in Tamil, it will convert it into Tamil. And then we'll convert that Tamil text into a target text language by using machine translation systems. For example, it's English, then it will be Tamil text into English text. Then that English text again will be converted into a speech format by using some kind of a speech synthesis system, which is called text to speech. So this is the traditional way of translating one language of spoken language into another language or target language. But nowadays, we are seeing that without using a machine translation systems, we are trying to convert the spoken language directly into another spoken language. That means the same speech, what I speak, it will be directly converted into another language speak. If I speak in Tamil language and it will be converted into English language without use of these machine translations and the text-to-speech synthesis system. This is the recent trend in the speech-to-speech translation systems. Speech-to-speech translations. You will find there are many research work in the direction of automatic speech recognition systems, where we are getting a text as the output for a given speech input. But in the speech-to-speech, the input is speech and the output is also speech, so the language will be different. That depends upon the applications. So now we will find the application of automatic speech recognition systems and also speech-to-speech translation systems in many of the applications. One is the interactive voice response, then language translation technologies, as I mentioned, one language to another language translated. It can be a what is called cloud-based spoken language translator, or we can say a standalone translators. So that depends upon the applications. So therefore, I will also highlight some of the advantages and the disadvantages of edge-based speech translators, speech-to-speech translators, and also a cloud-based speech-to-speech translators. You will also find this type of language translation technologies in the language learnings. Nowadays, we are going for online learning systems. So there is no way to understand, for example, something is printed in one language, or something I want to communicate to the native speakers or regional speakers where I do not know that particular language. So we can use that type of systems. That is one of the interface. It's called voice-enabled interactive interface. So, and also medical transcriptions. This is also one of the major application of this type of automatic speech recognition systems and speech-to-speech translation systems. So now these two technologies, ASR technologies and speech-to-speech technologies, that will be implemented either on a handheld devices or a cloud-based systems. But nowadays we like to use everything. So we like to implement these two technologies, everything on a handheld devices. But these devices are having some kind of resource constraints in terms of battery power and processor speed and other constraints like a memory. Okay. So, but if you see the recent trend in the mobile handheld devices, particularly smartphones, the memory and the processor speed is not a much problem. The major problem is only the battery power. So now that is the major limitation of this on-device automatic speech recognition system or a speech-to-speech translation system, which is also known as a standalone ASR system or standalone speech-to-speech translation systems. But if you like to use cloud-based speech-to-speech translation systems, in particularly that the cloud system is enabled with various kinds of speech models, spoken language models. Not only that, only specific target language. Because if I consider that all Indian languages, Indian spoken languages, let us take, if I consider 20 languages, then I have to create a 20 language models which need to be stored on my handheld devices, which is maybe one of the limitations because a smartphone also used for some other applications. So if I want to use cloud-based system where we will have all language models, particularly 20 language models, and there is no limitations in creating a large corpus-based language models, which can improve the accuracies in the case of speech-to-speech translations or automatic speech translations. But the limitation is that the network, again, the communication failure network coverage is one of the challenge. Okay, but each of these systems have own advantages and disadvantages. Okay, so now if you consider both deployment scenarios, one is cloud-based scenarios and standalone-based scenarios, or any kinds of applications. And the major challenge is that how to improve the automatic speech recognition system accuracies and also a speech-to-speech translation system accuracy in the presence of various kinds of noises. So therefore, we must understand what are the different type of noises that we can see in a realistic scenarios, because you cannot expect that this handheld devices or a cloud-based systems will be used in an indoor environment. It will be mostly used in the outdoor environment while traveling. You will try to set some things, or you will try to access some services while traveling by a car, while traveling by a train, or while traveling in a crowd area environment, or in a shopping mall environment, or in a coastal regions. So therefore, we must understand the characteristics of this type of background noises. So we classified this type of two type of noises. Sorry, classified this type of noises into two. One is short duration noises, long duration noises. Some of the scenarios you will find a noise burst that can occur yes, millisecond in terms of a 200 millisecond or 100 milliseconds or a 50 millisecond and 30. But there are some cases we can expect that longer duration of noises, like if you take a fan indoor applications. So therefore, we must know what will be the characteristics in terms of their durations of the noises. Okay, based on that duration characteristics, we can also choose some type of signal processing techniques to enhance the quality of the speech signals before feeding to this speech-to-speech translation systems. So now in the short duration noises, further classified into indoor short duration noise, outdoor short duration noise. You will find indoor like a door knob, object falling, then refrigerator noises, and then firecrackers, explosions. And similarly, the outdoor noises, similarly for a long duration noise, again further classified into indoor and outdoor, then fan noise, air conditioner noise, some kind of conference noise, forest noise, natural noise, transportation noise, like including car, train, and aircraft. So now we know this type of noises in a realistic practical scenarios. Now we have to improve the accuracy of the speech-to-speech translation systems. Even if the system is running on a cloud-based or running on a standalone, or it will be used for any kind of applications, because the user is going to provide a speech signal and a different background noise scenarios. So therefore, the quality of the speech signals that will be acquired before feeding to the systems must be acceptable, or we have to use a very high quality microphones, or we can say I can use this directional microphones, so that I can avoid the what is called intensity of the other background noises, other direction noises coming from the other directions, except the directional microphone, particularly directionals to the speaker mouth. Okay, so it's called. So how much very closeness? That closeness of the microphones also very important in understanding the level of the different type of noises. So level of the noises and mixture of the noises, which are most important when you want to develop what do you say high accurate translation systems. So now, what are the just I summarized now that impacts of the noises? That is the performance of the current ASR systems. I used this ASR because we are more familiar with this terminologies, but nowadays we are going for a speech-to-speech translation systems, which is highly impacted under different noisy speech signals, which I mentioned in the previous. Particularly, you will find that this type of devices most widely used in a traveling environment. Okay, so that can be a car, it can be any kind of a train, or it can be aircraft scenarios, or in a crowd environments. So now we have to see how to improve the accuracy of this type of ASR systems and speech-to-speech translation systems. And in addition to the natural sounds, when you want to use the systems under rain conditions or heavy wind conditions, then we have to understand the impact of this type of wind noises and rain noises that will impact the or degrade the performance of the speech-to-speech translation systems. So car and train aircraft noises which are unavoidable in a practical life. And we will find this ASR system has a poor word error rate and character error rate for severe noise speech signals that can be referred to as a false recognition rate. Further, it is difficult to achieve better enhancement results under different kinds of noises. So you will find there are many research groups will develop different signal processing techniques to enhance the speech signals. So they like a spectral subtraction methods or any kind of a decomposition methods or prediction methods. You'll find various kinds of signal processing techniques to enhance the quality of the speech signals. So now we cannot develop what is called a single signal processing techniques which can handle various kinds of noises, or we can say we cannot provide a better quality of signals under various kinds of noises. So in a particular noise, the noise itself varying over the period of time, and that's the one. Another cases, the different kinds of noises also. So now we cannot expect that one signal processing techniques can solve this type of problems in providing a best quality of signals before feeding to the speech-to-speech translation systems. So therefore, you will find that there are research groups and they are trying to develop a noise robust ASR systems. They'll try to incorporate a noise specific models into the speech recognition system also. So that they are able to improve the accuracies. In particularly for train car, they'll add this speech model, this noise model also. So, but we cannot expect that we'll still can have a better accuracies in all realistic scenarios. So now, as I mentioned that, why do you want to go for edge computing and cloud computing? Severely corrupted speech signals by nature man-made, unnecessary processing of a corrupted speech consumes a significant amount of power when we consider what is called edge-based speech-to-speech translation systems. So if we know that if the signal is corrupted with a train noise behind this noise level, then we are not going to have a better word error rate. Means I can say lower word error rate or lower character error rate. So in such a cases, if we have a system which can check the qualities based on the noise types, with their reference noise level, because each noise types we will have a different noise levels for a different word error rate. So we cannot say that, for example, noise level of I'm talking about relatively 0 to 1. If a noise level of 0.1 fan noise can provide a word error rate of, let us take a 2, or if I say train noise noise error of noise level of 0.1 can provide a word error rate of 5 also. So we cannot predict exactly that what level of noises we are going to have a best accuracies. So therefore, there is a what is called challenging in choosing that what is the noise level, what is the or in choosing the noise threshold level for each type of noises. Then we can just decide whether the signals can be further processed or it can be discarded from the speech-to-speech translation system. If by doing this way, we can reduce the energy consumption of, in particularly, edge computing platform. So continuous transmission of speech leads to incur more bandwidth utilization cost again. ASR software use, because we feel that this software is currently freely available. So we cannot expect that speech-to-speech translation system software will be freely available tomorrow also. So every processing, one can charge that if I process the speech signal for a 1 minute, 2 minutes, or 1 second, 2 seconds, we can charge for the utilization of the software. So if we can have some kind of a checking, what is called it checking, so we can avoid unnecessary utilization of a software for the case of a highly corrupted speech signals. So then cloud-based requires reliable internet connections. That is one of the challenge. And then battery lifetime, again, that's a major challenge for any handheld devices. So now I just summarize the existing automatic speech recognition systems, in particularly based on the deep neural networks. So you will find that there is a time frequency features, and then these are the different environments and the databases used for validating the what is called robust automatic speech recognition systems. So they showed the word rate of 5.76 on Aurora database, and similarly domain variant invariant speeches were proposed by this Hughes et al. In 2018, and they evaluated with Aurora and SIMI 4, and then word rate of reduction of 41%, Aurora data by 27%. Similarly, the LPC log power spectra is explored with deep neural networks and validated with this data set, and then they got a word rate of 5.3.76. So now, if you see this, there are many variants of a deep learning methods were explored in the literatures by combining with various kinds of existing features, because these features are well studied by using a traditional machine learning techniques. So, but they are just combined with the deep neural networks and its variants, and they validate with the same data set, and they try to see that how much the improvement in terms of word error rate with the baseline technologies, and how much the word error rate uh, for this type of recipe. So you will find different kinds of noises for each of the data sets. So now what you want to highlight here that even though they try to incorporate noise specific models in order to improve the accuracy of the ASR systems, but still they are able to get a word rate of 14.1 percentage by using this combining with the deep neural network and hidden marker models with the MFCC features on the Aurora database. So it shows that there is no possibility to further improve the accuracies of this type of automatic speech recognition systems, even if we combine with the noise specific models. So now to demonstrate that one, what we have studied in our lab, that we have used the existing Google-based translation systems. Then we created aircraft noises, train noises, wind noises, car noises, rain noises, fan noise database. These are really these background noises are recorded in real time by using some instruments. Then we normalized all kinds of noises, and then we have created this noise levels of 0.001, and that noise levels of particular noise sources will be added to the existing speech databases, and then we try to know what is the word error rate. So then we found that there is a limitations of the even the existing what we talk about Google Assistant or cloud-based speech recognition systems. So this column represents the noise levels, and this row represents a different type of noises. Aircraft noise, train noise, wind noise, car noise, train noise, and fan noise we are considered in our studies, and different noise level metrics. That's the one. Then word error rate we calculated, and then we can find that, for example, if we consider the aircraft noise, and then for the level of 0.1, the word error rate is 5.55 percentage. Character rate is 3.51 percentage. But if for the case of a train noise with the same level we are talking, no, because see, we are considering the level in the sense it's a maximum level, but the characteristics of this type of noises will be different. Okay, one will have a localized characteristics, one will have a uniform character, distributed characteristic in terms of your overlapping spectra, in terms of your non-overlapping spectra. Okay, but we are talking about the noise level in terms of a maximum noise level relatively. So you will find that even the noise level we see, which we assume here is 0.1, and it is going to it had a word error rate of 11.11 percentage, but for a same noise level, aircraft noise is 5.5, and similarly we studied for this, but you can find that for a rain noise and fan noise, the word error rate is 0 and character error rate is 0. So that means what for up to the noise level of 0.2 for the rain noise and fan noise, the existing ASR systems having a 0 word error rate and a character error rate. But if the noise level is beyond 0.2, we can see that there is a error rate, and then we can find that if the noise level is beyond 0.5 and 0.6, 0.7, 0.8, 0.9 and to 1, we can find that error rate is final. So it means that the existing ASR systems cannot what is called provide the accurate speech-to-speech translations or automatic speech recognition system, accurate textual information for a spoken language under these kinds of noises. If the noise level is beyond, we can say here borderline is I can say 0.4. So this is the baseline study. Okay, we can use this as a reference if we want to develop any speech quality assessment. So now we are studied with this existing methods, existing ASR systems, that yes, there is a scope for developing a pre-processing techniques which is known as a speech quality assessment, which can check the quality, and then we can that based on the quality of the signals, whether we can pass through the ASR system or we can discard from the ASR system, and so that we can have an advantage of energy consumption reductions and by discarding the similarly character signals. But one can argue how they are going to how do we design, how do you what is called fix or optimally choose the noise level for various type of noises. So therefore, we have to combine the speech quality assessment with the noise recognition systems. So we have to recognize the type of noises first, then we know, yes, for this type of noises, and by using this chart for this type of ASR software, we can fix, yes, if the noise level is beyond this, and anyhow, the system will not provide any kinds of accuracies. So I can just do the simple noise level threshold based method for speech quality assessment if I can know the type of noises. Okay, but recognizing the type of noises also one of the challenging. It can be mixer of this type of noises also, not only one single noise sources. It can be in a practical cases. It's a mixer of a many noise sources. Okay, so therefore, still this is a challenging problem. It's a continuous research task. So just I plotted here to demonstrate the fan noise and this one. So you can find various curves in the character, whatever I demonstrated in terms of table. Here we can see in terms of a curve, we can find that. So behind this 0.4 and for all kinds of noises, the existing systems gives very high word rate and character error rate. So then the different speech quality assessment methods are developed by using a time domain waveform and spectrum features in our laboratories based on the 1D CNNs and 2D CNN classifiers. And then we also proposed some set of pre-processing and feature extraction techniques. And then we have tried to construct this 2D CNN, 1D CNN architectures to develop a speech quality assessment method. So now, one of the main challenge for this the development of speech quality assessment is creating a database. It's not easy that I just record my speech signals in a cloud environment or outsourcing environment, or so I can just use the noisy signals list. So because we are going to check the quality of some duration of your speech segments. Let us take, I'm checking every, for example, 50 milliseconds or 100 milliseconds. So now we do not know that 50 milliseconds or 100 milliseconds of the segments are noise free, even though the signal is recorded under different noise conditions. So therefore, creating a database, which itself is one of the challenges. So therefore, we have made what is called trained in two ways. One is called blind training method, where we collected a different type of noisy speech signals which are available in different social websites, and then we extracted the audio part from the video also. And then we know that yes, this recording is character the train noise, and this recording is character the wind, and this one. And that is one type of training process, which is called blind training process in our work. And then another database we created, which is called an engineered training process, where we collected only the noises. There is no speech in that our noise recordings, but then we normalized it, then we injected with a different level. Then we have covered all levels of noises for various kinds of noises in the speech signal. Then we have used for the training. Then we have seen the improvement in the accuracies of the engineered training process as compared to the blind training process. Why I say engineered and trainings, you can understand now when you talk about engineered features and we say traditional machine learning. When you talk about handcrafted features, it's traditional learnings, but we are in the CNN, we'll say that there is no handcrafted features. The network itself can extract the features, but it's not possible if we cannot have we can say clean database. In the clean database, in the sense, okay, that yes, all the portions of the speech signals are corrupted with the noises. It's not that a single segment is a noise free. Otherwise, the systems we cannot provide the best model for each type of noises. So therefore, we have made it a true training process. One is engineered training process, and another one is a blind training process. And then we have tested both the trained models in a realistic scenarios. It's not that we trained with only engineered data set we trained with the test what's called blind training. We use the blind training data sets also testing the engineer training models. Then we found that engineer training process, the way we discussed in the previous slides in terms of the noise level for various kinds of noises. So we have seen that the performance of the speech quality assessment can be improved. So just as I mentioned that there are two ways we can do when you doc. There are many ways because there are many variants in the deep learning. But I just focus with only convolutional neural network based methods. And one is with time domain features and the MEL frequency septal features. And another one is spectrogram features, or we can say image features. It's not only spectrogram, one can use a scaleogram, one can use MEL spectrum also, one can use any kinds of spectrogram, time frequency spectrogram features. But we have used only STFT features spectrogram that is combined with the 2D CNN. So we also studied the performance of these methods and based on different frame durations. One is 100 milliseconds, 250 milliseconds, 500 milliseconds. And we also studied with the blind training process and the engineer training process for developing a accurate and robust speech quality assessment method. So you can see that the flow for the training phase, and this is the flow for the testing phase, and there is a pre-processing, feature extractions, and convolutional neural network. So here there is no much pre-processing in terms of filtering. Pre-processing in the sense here only is a blocking. Okay, we are framing, or we can say block processing. Then feature extractions, as I mentioned, we used the time domain features and the MEL frequency spectral feature, MF60 features that will be will be fed to the convolutional neural networks. Then we created a noise-free speech model and noise speech models. So this noise speech model includes all kinds of noises what I discussed in the previous slides. And similarly, same process will be continued, and then we used these models and then testing. We use only noise speech segment and noise-free speech segments. As I mentioned that if one can develop a noise recognition system, or you can say first of all detecting the presence of noise in the speech signal, and then one can develop what type of noises is added to the recorded speech signal. Then you can choose symbol threshold that I mentioned in the what is called threshold based error comparisons. That's a one way of one approach. Another approach is just only two class problems, whether it's a noise segments or noise free segments. So just moving to the convolutional neural networks, and I'll just introduce the basics of a deep learning. You know that deep learning is the multi-layer neural network that contains two or more hidden layers. But we know multi-layer neural networks is famous for last 30 years, and to solve the problems of a learning rule of the single layer neural network by the back propagation algorithms. But there are some limitations with this type of networks. So that is with additional hidden layers, the back propagation training often results in a poor performance, and the deep learning can provide a solution to these problems. Because see, when you talk about a traditional machine learning approach, we extracted the specific features which are relevant to the auditory systems. Okay, in terms of your speech quality checking, I'm talking. What type of noises are it? The way the human hearing systems are able to distinguish, okay, that yes, this signal is correct with the train noise. Yes, this signal is correct with the car noise. But that also has a self-learning process with the visual features. Then only our brain system able to say that yes, the speech signal, this is the speech, and which is correct with the train noise, which is correct with the car. But we have to make the system, computation system has to perform this similar task. But in the brain systems, so we have extracted, we can say unlimited features that still we do not know that we want to obtain by using this type of deep neural networks. So in the traditional methods that we extract only specific type of features, which are relevant to the specific type of noises and the speech portions. Then that specific features will be used in the training phases to create a models for a speech recognition systems, or create a model for checking the quality of the speech signals. But traditional way of deep learning, recent deep learning methods say that yes, you can just feed whatever the high resolution data which we are having in the MFCC, because you see MFCC also filter banks are used. For example, 13 filter banks are used. They used to get delta features. Okay, velocity feature, acceleration features were derived. So total 36 features are used in. But filter bank, because this type of restrictions were there because of the limited computational hardware in the first years of research. But nowadays we have unlimited hardware, computing hardware, high performance computing hardware. So therefore, we can use even high resolution MFCG feature. We can increase the filter bank. That also we carried out. Not necessarily that we have to follow only 13. That, see, we studied with the lowest, what is called 8 kilohertz sampling rate signals, which is called telephone speech for a ASR system. But nowadays we are going with the 16 kilohertz. But in between, now currently we are going with the high resolution speech signals because we have a more flexibility in the high performance computing hardware and cloud based what is called systems where it can handle the high energy consumptions also. So therefore we are not bothering about resolution of the speech signals. Now we have high what is called high resolution in terms of sampling rate very high because that sampling rate can capture even fine variations of the speech that is introduced for each of the character sounds, each of the sounds. So that's the one advantages nowadays that we have, that we can increase the resolution of the features. So therefore you can find people who explore the bell spectrum. So similarly, instead of extracting the audio features which I discussed in the previous presentations or previous talk, that spectral entropy, spectral flatness, spectral brightness, spectral flux. These are extracted from the certain Fourier transform. Now we can directly feed that spectrogram, which is the 2D representations of the speech signals, and x-axis is the time and y-axis is the frequency, and then at particular time, what is the frequency, how much the energy that we are getting in a different color. So that will be used as an image, and then we are feeding to this type of with the more hidden layers or more deep neural networks. We try to extract all kinds of features, and and it will go for optimizations, and it will try to give a best accuracy. That is we know from the past studies. Therefore, we are trying to use this deep learning based methods without extracting a specific type of features, and directly we are feeding the high resolution feature map, and also that. So in the CNN also we have some kind of feature extractor. Okay, it's also similar to that, but it is not. It does not require any, I can say, subject knowledge. People are saying, because I need to create only the database. Okay, and then I can feed to any kind of very good tools of deep learning neural networks. Any kinds I can use variants of a deep learning, and I have to create only database. It gives a result. So I do not require much knowledge about what is MFCG, what is LPCG, and what is audio features in the case of deep learning based speech processing techniques. So what are the limitations that we are seeing in the case of a pack propagation algorithms, in particularly this multi-layer neural networks? One is the vanishing gradient and overfitting and computational load. So these are the difficulties that we are seeing in the existing, and that can be further improved by using these deep learning neural networks, and including how to solve this vanishing gradient and how to solve this overfitting and the computational load. So the solution to this vanishing gradient is done by using the rectified linear unit, the function as active functions, activation functions. So the sigmoid functions limits the loads of the outputs to the unity, but you can find that ReLU functions, ReLU functions most widely used in this application of DNN based methods. Then how to avoid the overfitting? So what is the exact, there is option for a dropout, and in that way we must understand what it means overfitting. Okay, so the reason that the DNN is especially vulnerable to overfitting is that the model becomes more complicated and includes more hidden layers and has more weights. Okay, so therefore we can include some kind of a dropout layers, and which can reduce the overfitting and also a computational load, and that can be solved with the GPU and batch normalizations. So now, if you look at what is the actual architectures of the, or we can say the components of a convolutional neural network, I'm just giving a brief introductions. Okay, so before convolutional neural networks, we can say the feature extraction has been designed by experts. That's how we can say experts driven features, or we can say handcrafted features or engineered features. of a specific type of signals or areas, which is independent of a machine learning. So machine learning is not dependent on the feature. It is independent. What is a feature extractions? I am extracting and then I am using a machine learning for only for a classification purpose. But in the traditional, in the recent convolutional neural networks, we have a feature extractor. So convolutional neural network includes the feature extractor in the training phase rather than the designing it manually, which includes a fully connected layers, activation function, convolution layers, and polling layers and normalization process, that patch normalization process. So just we understand what is convolution layer is similar to the whatever the convolution that we studied. Convolve the filter with the image and slide over the image space any computing the dot products. That's all. Then we have to choose what is the kernel for this. Then once you get the convolution layer maps, or we can say feature maps, we are talking about the pooling layer. Is a way to reduce the size of this feature maps. Okay, there are many types of means operations are used in the pooling layers. Maximum pooling or average pooling, or sometimes we can see that global pooling process. And there is a component which is called activation functions, as I mentioned. It introduces a nonlinearity to the model, which allows it to learn complex function mappings between the inputs and the response values. Okay. Similarly, batch normalization, it normalizes the outputs of a layer, so they have zero mean and unique variance. So that helps to reduce the internal covariate shift, or we can say improves the optimization. So these are the minimum things that we need to know what is called about the components of the convolutional neural network. So after that, we have to design. We have to know what will be the how many layers are required. That's all research. So we cannot say that still the system can decide what we can do. But people are using the existing what is called training networks, and they are trying to get. But there are limitations for each of the methods. So for this studies, we used a database which includes total number of sets of 25 and the total number of speakers 6, and duration of each set is 50 seconds, and the total synthetically added noise is 6. Audio format is dot wave, channel is mono, and as I mentioned, we used 16 colors and bit resolution is 16-bit. And what are the pre-processing that we performed? Because you know that we are recording a speech signals by using a different recording devices from the different speakers, and we do not know what is the where is the location of the microphones when we record the speech signals. So we have proposed simple pre-processing before creating a what will say image, okay, or a MFCC and feeding to the CNN networks or DNN networks. So noise-free signals, we remove silence, resampling, normalization, segmentation. Then we created noise-free speech signals after pre-processing, and then background noises and the resampling, normalizations, and then we added the noises with the different noise level. Then we perform segmentations. Then we used that as that segments as for a training purpose. Because as I mentioned, we studied with the 100 milliseconds, 200 milliseconds, 500 milliseconds. That's called segmentations we are here. Okay, that's not equal. That's not exactly voice active directions. So now, what are the features that we used? One is the MFCC features, well frequency spectral features, which is well known in the speech processing system, speech processing research. And then we also used spectrogram. Spectrogram is plot of the relative energy content in the frequency at different resolutions. So here I plotted the spectrogram for various kinds of speech signal character, the different noises. One is noise-free speech signals, and this is the one. And then speech signals character of the aircraft noise, and that is the this one. And the speech signal character of the train noise, and the speech signal character of the fan noise, speech signal character of the car noise, and speech signal character of the wind noise. So now, actually, just say, even though the DNN is going to do everything for us, to extracting the features and creating the training models and giving some accuracies, but we should also understand the spectral natures of this type of signals with the various kinds of noises. And by as a researcher, we must understand. If we can understand, then we can understand the failure of the DNN also. Why the DNN is not going to give a result? Is there any problem with the feature which we are feeding as in terms of spectral features or spectrogram features or MFCC? So therefore, even we say that manual extraction is not required, but understanding each type of signal characteristics is most important. It's not only in the time domain, it's also in the frequency domains, because if one can understand the characteristics either in the time domain and frequency domain or both in the time and frequency domain, then we can also develop some energy efficient deep learning based methods, a speech to speech translation system, or we can say deep speech to speech translation system in an efficient way. So therefore we have to understand. So understanding the characteristics of this type of speech signals uh, before developing any system is most important. That can reduce the energy consumption, because we can provide some kind of intelligence to this type of deep based speech to speech translation systems. So this is the simple block diagrams with I plotted here. This we used 1D conventional with the filters is 27, kernel size is 3x1, and then maximum folding we used, and then we got the noise free segment and the noisy segments. And so these are the specification of 1D CNN. So for 100 milliseconds, and then we can see that total number of parameters is 13,000, so 60. And these are the different number of neurons and each stages, and this is a kernel size. So these are the specification of our 1D CNN. So for 500 milliseconds, so it increased to 49,000, but for a 250 milliseconds, it increased to 26,000. Okay. So yes, this is for MFCC features, and we used for this one is we have combined all the cases. Okay, so 3,000 here, and then we also what is called, this is the block diagram of your 2D CNN based speech quality assessment for by using spectrogram. We have not studied with the Bell spectrum. We studied with the MFCC features. So therefore, we combined with the 1D CNN. But in this case, we used spectrogram directly as an image feature, image map, okay, to this 2D CNNs, and this is our architectures. And then this is the different layers with the filters, which are very important when you want to demonstrate or when you want to compare the what is called specification of 1D CNN and 2D CNN in terms of computational operations. So this is for spectrogram features. And here you can find that what is called it is the total parameters. So 83, we can say 83,000, sorry, 8 lakhs, 8 lakhs, 31,000 parameters. Okay, in the case of 2D CNNs. But in the case of 1D CNN, with the MFC features, the number of parameters are very less. Okay, so now we have just for a time domain waveform, because please remember, we have carried out the 3 studies. One is time domain waveform, then MFCC features, and then spectrogram features. So this is the result of 1D CNN for the time domain waveform. It's a raw data directly used without extracting any features for different block size, frame size, to 100 millisecond, 250 millisecond, 500 millisecond. This is the confusion matrix. Okay, so now we can see that for different frame sizes, we can see that overall accuracies for 500 milliseconds, which because some of the noises will have a longer duration, some of the noises will have shorter durations. So therefore, we carried out this frame duration wise, frame size wise accuracy study, because we can know that how much is the variations in the accuracies, because some kind of noises will have a shorter durations, some kind of noises will have a longer durations. So we have to know that what will be the accuracies for various kinds of noises. So we can see that 500 milliseconds, the sensitivity is 99.43, and sensitivity in the sense that in detecting noise-free signals, and festivity is nothing but detecting the noisy speech signals, which is a 92.19%. Overall accuracy, so 94.2%, 1.12%. So this is 1D CNNs by using MFCC features, and here you can see that it is going to give only 87%, but for 100 milliseconds we have observed that 94.18%. So that means sensitivity of 1D CNN with the MFCC feature for 100 millisecond is 99.59% as compared to this. Okay, so even though it is giving 99.43, that means there is advantages for the use of MFCC for checking the quality of the speech signals, because it is going to we are using MFCC, but the frame size is 100 millisecond. But if you see our total parameters which are there in the trained model is much lesser as compared to this 250 and 500. So that itself shows that the computational resource requirement will be further reduced, because we are able to get that sensitivity of 99.59. But whatever the specificity is here 92, but here 80.76, because as I mentioned, some noises will come in the longer durations. So that information may not be able to capture by the systems. So therefore, there is a trade-off. Okay, what will be the frame size and in terms of with respect to the sensitivity in correctly detecting the noise-free speech signals, and specificity in correctly detecting the noisy speech signals. So as I mentioned, this 2D CNN was the performance of the 2D CNN with the spectrogram features were studied with the two training process. One is blind training process, where we just extracted, we have what is called downloaded many audios from the different sources, and then we have seen that yes, this audio is corrected with the train noise, this audio is corrected with the aircraft noise. Then we blindly segmented and given to the training system, it's a 2D CNN system to create a model. And we have not done any kind of processing of that signals. So that is called blind training process. So in that case, this is the confusion matrix. And then in terms of numbers for a blind training process, NFC is noise-free speech segment, and this is a noisy segments. So we can see that sensitivity for aircraft noise is only 58%. In the sense, under aircraft noise conditions, the sensitivity of 58.62 represents that correct detection of a speech sounds, but 100% in the case of a noisy speech. So similarly, 78.8, 78.53, 80.08. One can argue that can you tune the model parameters in such that we can bring this one together? But still, this result shows that for some case of noises, we are able to get 80.08%, but 96 we are 96, but we are getting 8. So if I try to do this type of fine tuning of optimal parameters, then there will be a reduction in the other sensitivity parameters. So therefore, as I mentioned, if one can detect what type of noises which are corrupted in the speech signal, then we are able to have some kind of a noise specific model based this type of quality checking, or we can say assessment techniques. So now we carried out this blind training process for various kinds of noise levels. What we did here, we used the what is called publicly available noisy speech signal, noise-free speech signals in the training process. Then we created a synthetic noisy speech signals. Synthetic noise speech signal in the sense, we have a speech signal, we added realistic noise only. We added realistic noise, but which we call it a synthetic with a different level to understand what is the accuracy in terms of sensitivity, or we can say overall accuracy. So we can find that for aircraft noise, with that blind training model, with the blind training models of noise-free speech segment and noisy segment, and we are able to get these accuracies, what is called reductions. You can see 91.67. Then if the noise level is coming at 26.86, it shows that the blind training process, the blind training way of generating a model for this noise-free speech segment and noisy speech segment may not give best results in terms of accuracies in detecting the noise-free segment and the noisy segments. Okay, so that also we observe for all kinds of noises. So therefore, we move to a engineer training process. This is the curve. Okay, in terms of plot waveform, I can show that sensitivity and specificity, and I can see there is a trade cross section point where we can say up to that noise level, we are able to get some trade-off results in terms of sensitivity and specificity for a blind training process. Okay. So therefore, what we did that we have created a noisy speech signals with the various kinds of noises with the different levels, and then we used that database for creating a noisy speech model by using 2D CNN and with a spectrogram features. So now in that case, you can see that the accuracy of this one, it is slightly better, 80.12%, 94.0. In the sense, detecting the noise free under aircraft noise conditions. Detecting this one, that's a sensitivity, specificity, separately we studied. And then we also carried out. So now still you can see this detection performance slightly improved. Okay. So you can find this, it is going to up to 100% here, but still you can see that up to this noise level. So that means instead of degradations of this type of performance, in the case of blind training, you can see that. So here you can see 91 point this, sorry, 94 point this, yes, small variation. Yes. So now we can see that variations in the detecting a different type of noises with a different noise level, because we have used a synthetically generated noisy speech signals for creating a model, and we tested with all the cases, whether it's a what is called a downloaded noisy speech and also a synthetically created noise speech. This is a plot. So now we can see that blind training and engineered training, the improvement in terms of sensitivity and specificity of a noise type, noise, each kinds of noises, and then overall accuracies. Average sensitivity is 90.92% and 98.44%. 96 point overall accuracies, average accuracies 96.44%. In the case of engineered training process and blind training process, but the testing samples are same for both the cases. Please remember that's the one. So this is the architectures. We can see that 2D CNN models we created. And what we have done that we also studied this proposed system in real time, and then in an office environment, we use the same sound and we developed the interface because we should not feel that everything is synthetically generated, but we tested in a real time, and since it was the MTech thesis, so that's why we have just limited data set at that last minute we had. And then we can see that accuracy is 91.66% and sensitivity is 91.66 in the office environment, and specificity is 83.33. This is in terms of speech quality assessment. It not belongs to any kind of noises. Only 2 class problems, and the overall accuracy is 87.50%. Okay, so these are the references that used for this research work, and so thank you for listening the sections, and I also thanks my students for her contributions during the MTech thesis work. So I can take any questions now.
Thank you, sir. So participants are open to post their questions. So you can unmute and ask questions if any.
Any questions related to this presentation?
Hello.
Yes, yes. Please.
Yes, sir. I have a question. When we are doing the speech, when we are dealing with speech, most of the time we are doing the short time analysis in the range of 10 millisecond to 50 millisecond. But when we are dealing with the noises, we are means we are doing experiment with more than 100 millisecond. So
Yes,
what
yes.
is the difference between that? Why we are taking and while
Actually,
taking 100 millisecond, our signal may be non-stationary. So is there would be any effect on the performance.
Yeah, see, these are the different kinds of noise sources, okay, that we can see in practical. So there are impulsive noise. That's called click and pop sound. In the old recordings you will find very short durations. So you will find in milliseconds, 1 millisecond or 2 milliseconds. There are some noises, it will be at 20 millisecond, 10 millisecond. There are some noises which can extend till, I'm talking about the characteristics of the noises. It can, if you want to capture the full information of that noise, then it can be at 50 milliseconds or 30 milliseconds, 20 milliseconds. As you said, in the speech recognitions, we are interested to know to capture that phonetic sounds. So therefore, we go for segment analysis or supra-segmental analysis. It will be 30 millisecond, or it can be 20 millisecond, or a 10 millisecond. Our objective is to understand, to capture these phonetic sounds of this. But in this case, even though for example, here we carried out three methods. Okay, one is time. What is called time domain, raw data feeding to the system, that is 100 millisecond, 250 millisecond, 500 millisecond. In the second one is MFCC feature. In the MFCC feature, even we gave 100 milliseconds, but we followed that 30 milliseconds, 20 millisecond concept for a MFCC, that divisions of creating a feature map. In the case of a spectrogram, there also we are choosing, if you see the spectrogram, no?
Yes, sir.
Yeah, the spectrogram. Yes. So here also we choose the frame size actually. Even sorry, we can say a segment size. Frame size is 100 milliseconds, but within this 100 millisecond which I plotted here, no, you will find these are various kinds of blocks, various kinds of this one. So you will find what happened. This is 100 millisecond, next 100 millisecond like this. So now you within that 100 millisecond, I have taken a small window size with the Hamming window, and we have calculated the spectrogram. So it is automatically capturing that small durations noises, short durations noises also. Therefore, we are able to get this one. Okay, it's indirectly captured. That's why they say it is not manually. We have not done it, but the spectrogram, when you want to plot it, spectrogram is you are plotting for. You can plot a spectrogram for 100 milliseconds, but within that 100 millisecond spectrogram, you are trying to capture what? You have to choose the window size. You are using the overlapping also. You are using some windowing also to avoid the what is called discontinuity leakages. So we used a Hamming window, and then small size 20 milliseconds we used, and then we have used overlapping of 1 millisecond, 2 milliseconds. Then we are able to get this type of spectrogram. So the spectrogram, this image itself has all this short duration information also. But there are some applications you will find they take it 30 milliseconds, then they will take a Fourier transform of that 30 millisecond, then they will measure what is the spectral flatness, spectral centroid, then they will use that feature, one features. For example, spectral brightness is one value, spectral flatness one value, spectral flux is one value, spectral centroid is one value for that 30 millisecond. For that Fourier transform of that millisecond, one value only you will get. Then they use the machine learning algorithms to identify what type of noises. That is also you can do it. But now we are moving towards what you will say what is called machine-based feature extraction techniques. Now the question is that what will be the small window size that I need to choose for each of this frame when you create a spectrogram? One can study, people will further study. So I used to get 20 milliseconds, and with the Hamming window to get this spectrogram, even though it is 100 milliseconds.
Okay, sir. Thank you, sir.
Yeah, thank you.
So any other questions? Okay, so one question is there in the chat box. I will read it out. So text to speech conversion. Okay, in this case can be converted text into spectrogram, and then we can feed it as input to CNN. Will it work, sir?
What is that? Can you repeat the question?
I think the question itself is wrong because you cannot convert text into a spectrogram.
No. Can you read the questions actually? Can you read?
So he's asking like in text to speech conversion. So can we convert text into spectrogram? and then we can feed it as input to CNN.
Yeah, you are correct.
The question is wrong actually.
Yeah, no, not like that. So, yeah, in general, you can use image as a speech, sorry, spectrogram of a speech, then you can convert into text. But the text is a synthesis process. So
yes, that's
yeah,
it.
so there are deep learning based to synthesize, okay, where we have to create a what is called a speech corpus, for example, 24 hours of covering all the information. Then you use it to feed to the deep learning with your text information. So we are able to get the TTS by using deep learning, but not by using image features of your text.
Yes, Naseem, can you read it out? What is your question? So you can unmute your mic and ask.
Yeah, any can please ask the questions. If you have any questions related to this, please. You can unmute, you can ask any questions.
Yes, Naseem Babu, you can unmute and you can ask. Okay, so he's not responding.
Yeah. So there are I just want to conclude that nowadays deep learning is explored for the existing ASR system framework also, deep learning based automatic speech recognition system, which translate the speech into text. Then there are research components. You will find the researchers working in the direction of developing a deep that is called waveform based. Okay, developing a waveform based deep learning, or we can say deep learning based text to speech synthesis system. And you will also find there are people working in the direction of deep speech to speech translation system. Directly, you will try to get the bilingual corpus and spoken languages and try to feed to the systems, and which will, if I speak in, if my spoken language is in Tamil, automatically it will be given in English, or if my spoken language is in English, automatically it is given in Hindi. There is no machine-to-machine translation system and text-to-speech synthesis system. I also highlighted that yes, we can train the systems by using a time, what is called a time domain waveform directly with the raw signals. We can also use traditional MFCC features such as feature vectors, and we can combine with the 1D CNN, or we can use null spectrum by having more resolutions, and so that we can extract that feature which we missed in the conventional machine learning systems. Or we can use spectrogram, we can use scalogram, you can use any kind of time frequency images of your spoken languages to convert a speech to speech or text to. But here we highlighted that yes, existing speech recognition systems also has the limitations under various kind of noises. And even though they claim it will work for under different noise, but if we try to use in a different noise environment, we are going to have more error rate and character rate. So therefore, assessment of speech quality is most important, and it can be used for what is called requesting the user to re-utter the sentence. So if the speech is if the system detects as a noisy speech, and it will take please re-utter the sentence, please again speak. So these are the kind of intelligent system we can add to the existing what is called speech to speech translation system or a ASR system. Thank you.
So, sir, I have one question here. So there are other questions also.
I'm not able to see the chat box. Why?
You can see it. Maybe you can unshare it.
Okay.
Yes. Go ahead.
Yes. Yeah. In general,
Meera
all are
Devi,
using MFCC.
Dr. Meera Devi.
Is there any other suitable features for speech? Yes. Actually, we started to use MFCC and LPC. Actually, I can say in general because that has interesting characteristics. One is called LP model. It will lead to a synthesis of it's called inverse filtering problem. Okay. So therefore, the formats of that speech which are relevant to the sounds which we produce, it's related with the LP or LP spectrum. So therefore, we started using LP extensively. MFCC is related to the auditory perceptions. Therefore, we used MFCC and LPCC extensively, and some are variants as also that perceptual coefficients. There are many variants of MFCC and LPCC which are widely used. because of that. But these are explored with the constraints of the limited hardware. In olden days, if you see previously, I went the started speech recognition system for telephone speech, but it is restricted with only 8 kilohertz. But 8 kilohertz speech signal itself will not capture my fine variation information, which I utter some sounds in a different high frequencies, which may not be present in 8 kilohertz, but it may present in 16 kilohertz or 44.1 kilohertz. But now we have flexibility in the hardware, processing power and processing energy, and also energy. So therefore, we can have high sampling rate also. So MFCC is limited to the less number of filter bank. That is also with the constraint with the hardware. Now one can explore the MEL spectrum. Instead of MFCC extracting filter band, calculating energy for each of this filter band, and then deriving a delta feature, delta features, then we combine with this. But now we have flexibility in terms of hardware. So therefore, we can have high resolution in the data, time domain of the speech signal, and also high resolution in the MFCC spectrum or any kind of spectrum. So now, therefore, spectrogram become a most popular nowadays. MEL spectrum, spectrogram, and other time frequency spectrum. You can say spectrogram images. It can be a Fourier transform spectrogram, STFT traditional way I'm saying, or wavelet-based scaleogram, or any kind of spectrogram when you derive it. There are many limitations in the spectrogram also. So that can be used as a 2D images. It's a images to the this type of DNN. So therefore, the DNN open a mini again that exploring the features of a spectrogram. Okay, there are many other features, image features, spectrogram features, time frequency domain features. I think is it clear to you? I think I answered to the questions. So you can just unmute. You can also interact. There's no issue. Okay. Yeah. So in case of text to speech, most of the time generated speech is robotic. Would you please mention some points to make speech natural? Yeah, actually this is also many directions. So actually text to speech, as you said, it's a robotic in the sense you will not find the actual accent. Okay, some kind of, they say the variations, the way I speak now in the same sentence, I can provide some kind of accents. You will not get that naturalness. So that is always there. But we are able to, most of the applications where we use voice processing system, we are just compromising the naturalness actually. We are just looking for intelligibility. Naturalness and intelligibility is most important way to test this type of synthetically generated speech signals. But when if somebody is calling me and is calling from some environment, trained environment, I am attending the call, still I am trying to perceive what is speaking. Because I am happy with that, but I want that communication is most important. So therefore, we do not more focus on this type of intelligibility, what it says, or naturalness. But if there are many groups started how to how to incorporate all this naturalness, the way I speak, the way some actor, some eminent speaker speaks. So there are many people are working in this directions, adding naturalness to the TTS systems. So as I mentioned, there are two tests is used. One is naturalness test and then intelligibility test. But what we want commercial, we have most of the applications, we want the information. So therefore, we do not give much importance to the naturalness, but there are some people working in these directions. But it's a challenge, but still you can make it for what is called eminent specific, some speaker specific. Yeah, any other questions?
Yes. So any other questions from the participants? Sir, one question from my side. So since you used speech quality based speaker or speech to speech conversion, right, under different noise scenarios, so the results you showed, that is for the speech to speech conversion, or it is
No.
for
the result
noise
is
analysis?
The result is stored for automatic speech recognition. It provides the text. We use the Google Assistant and also base ASR, which we developed in our lab in one of the project. And so where we gave a speech and we got the text, then we calculated word rate and the character rate. Then we listed yes. Even though if we go with the what is called well-known technologies like a Google Assistant or Google interface, and there is a limitations that we will not get a what is called accuracy for ASR under different kinds of noises, but that is also limited with the different kinds of levels of the noises that will vary. That is the study first we carried out to demonstrate there is a scope for this.
Okay, sir. Yeah. Okay. Thank you, sir.
Yeah, thank you.
And thank you all for attending this session. And thank you, sir, for giving us your precious time for this session. So we thank you all. And there will be valedictory session at 1:30. So please be ready for the valedictory session at 1:30. So this session is closed. Thank you all.
Yeah, thank you so much. Yeah, thank you.
Yes.
Thank you.